So Andy from OneHouse. Woo! I'll open your presentation of this. And let's see if it works. Yeah, perfect.
All right, cool. Can you guys hear me all right? All right, cool. Yeah, thanks so much, Brad. I'm actually really happy to go right after you because he gave the best intro to table formats in Spark that plays well into this. So I'm gonna kind of continue on the same theme of data lakehouses and working with Spark and talk about some learnings from at OneHouse, how we were able to 3x performance of Spark. And hopefully there's some takeaways that folks can bring to their open source Spark deployments as well. A little bit about me, I'm a product manager at OneHouse. Previously worked at an AI startup called Dashworks, and before that was at Google on some ads and MLOps products. A little bit about OneHouse right before I dive in. We are a full data lakehouse platform. So we offer everything from ingesting data into the data lakehouse, from databases, Kafka events, files on cloud storage. We also allow you to ETL that data, so you can use SQL and Spark jobs. We optimize the tables for you, and then we help you expose it to any catalog and any engine. Of course, under the hood, it uses Spark and open table formats like Apache Hudi, Iceberg, and Delta Lake. So before I dive in, I want to talk about something that we released earlier this year, and this is really what led to some of the insights in the presentation. We built the Quantum engine, which is a fully Spark-compatible compute engine that was able to blow performance out of the water from some of the existing leading players. In our benchmarks, we found that running Quantum, we were able to significantly improve on the price performance versus many of the leading Spark platforms out there. And I'm going to talk about some of the strategies that we use to get there. So before we dive in, I want to just give a quick intro to ETL. I guess before that, how many people in this room are using Spark regularly? All right, a good amount, let's say 50, 60%. So if you're using Spark, you're probably doing ETL with it, extracting data from sources, transforming that data into tables, and then loading that data into maybe some file storage. Now, the ETL process, the reason I talk about it is because you can kind of break it down into different sections, and different sections kind of have different requirements. The extract and the transform tend to be computation heavy. You need CPU, you need memory, you're doing a lot of reading and processing, whereas load is more IO heavy. And load, the load step often gets overlooked. People don't really think about that when they're trying to optimize Spark, but this actually can contribute significantly to your Spark costs. What we found with our customers is actually, we see about 40% doing mutable workloads, which are very load intensive. You know, you're writing files, you're rewriting a lot of files when you're making updates, whereas the extract and transform heavy append only are about 60%. So we are seeing a much higher rate than most people think about with the mutable workloads. This is backed up by the open source data too. If you look at the leading data lakehouse projects, Apache Hudi, Delta Lake, and Iceberg, we see a lot of workloads that involve merge into, delete, update, in many cases more than 50%. And that is because, you know, we have a lot of workloads where you're treating a data lakehouse as a transactional layer. And also we have more and more requirements for deleting data with regulations like GDPR. So how did we get to this point? How were we able to 3x Spark? What we did is we vertically optimized the stack. And this is the real key point that I want to talk about today. And the main takeaway I want to give is that if you think about all the layers in the stack and optimize them one by one, you can get really significant performance gains. So at the top is that engine layer, the Apache Spark layer. I list out a few of the optimizations we do in each of the layers here. So you have things like vectorized execution, you have dynamic allocation, which are ways that you can use compute more efficiently and that you can actually reduce the data processing and the objects that you're creating. Next layer is the Lakehouse platform. So at OneHouse, we use Apache Hudi under the hood, but I call it a Lakehouse platform, not a table format, because the Hudi library allows you in our next release to actually be able to write in both Iceberg and Delta Lake. So kind of abstracting away the table format layer and giving you the library that you need to efficiently write to a data lakehouse with things like indexing, similar to what you would find in a traditional OLTP, which allow you to process data more incrementally, as well as asynchronous table services. Like I heard someone asking about how do you compact small files. That's what those table services can do. They're out of the box with Hudi, as well as merge on read, which can really help you with those mutable workloads and streaming style workloads. The lowest part in the stack here is the file format. So as Brad mentioned, you have these table formats, but under the hood, they're really just Parquet. They're a columnar file format with some metadata on top of them. So we even went into the Parquet layer with vectorized columnar merging, and there's optimizations that you can do here as well to help accelerate things even further. So I'm going to start by talking about some of the Spark optimizations. We can learn a little bit about vectorized execution. So this is something that's becoming very popular in the industry, doing vectorized execution. As Brad mentioned, Spark is built on the JVM, but what people have found is with native C++ implementations, they can get around some of the things that make Spark a little bit slower. So what you can do is actually push down the Spark operators to C++, and that allows you to process data column by column, as you see here, as vectors, instead of going row by row, which requires you to create a lot of objects and deal with garbage collection and all of that. So this can actually significantly speed up Spark workloads and help save on costs. And it's available actually through some open source projects like Data Fusion and Velox. Now, we looked into those projects and we did find a few challenges using those in the wild, which I want to call out. So these open source libraries are really cool. I think there's a lot of development going on them, but they're not yet totally mature. When we brought it to production customers, there were a lot of challenges we faced, like certain operators in Spark not being fully implemented and having to fall back, but sometimes jobs even failing or hanging, not falling back correctly. There's also sometimes limited write support for data lakehouse workloads. You know, sometimes with tables, you want to be able to do things like merge on read, which aren't always yet possible with some of these libraries. So there are ways to kind of optimize the libraries. I definitely recommend checking these out and trying to experiment with them in your own workloads. Now getting into some of the storage optimizations, I'll give a few examples of what we've done, and hopefully these can serve as some inspiration for everyone here. This is just an example of one of our customers who had a 30-minute latency. This was a very write-heavy workload, kind of streaming style, and they were dealing with over 500 node Spark cluster. So we're talking about real scale here. And the optimizations that we're going to talk about at the storage layer were able to help this customer achieve their goals with OneHouse. The first one is optimizing lookup costs for updates. So if you have update-heavy workloads on the data lakehouse, when you're updating a record, you need to do that match against the record key or the primary key, whatever you want to call it, and this requires a lookup. Now, with a typical simple index, you know, this might take, this is write latency in seconds, 14, 16 seconds in our example here, but we were able to bring that down significantly, down to 390 seconds with the record level index. So this is one of the great features that Apache Hudi brings in the open source, where you can actually get super fast lookups directly on a record with its primary key. So when you have to go in and you're doing a lot of updates, you need to check if a record exists so that you can merge on that record. This helps you do that much faster. And you can see here the impact. We're able to get 72% improvement in write latency and a 92% reduction in those data shuffles. Next one is random updates. So random updates are a big challenge on the data lakehouse. You know, we've moved to immutable storage on object stores, which means when you want to rewrite data, you can get really costly rewrites of files, and this leads to overall you ending up writing way more data than you want to. These are a few kind of common types of tables that probably many folks here have worked with. You have your dimensional tables, which are mostly random updates. You know, someone might be updating an address, and this could be any file in your database. You have fact tables, which are typically going to be, new data getting written, more append-only style, but we still see, sometimes there's late arriving data. Maybe like there was a transaction that happened, someone made a purchase and they realized that it was the wrong price. They need to go back and do an update. That might be a file that is somewhere deep in a partition. You don't know where it is. And then event tables are, typically like telemetry style workloads. These might often be append only. But again, you have those policies like GDPR, which require deletions. They require lookups and updates. So, random access is a challenge on the data lakehouse. And a way that you can solve this is by using techniques like merge on read. So merge on read is a way to amortize those file rewrites. Instead of when a new file comes in, having to rewrite entire partitions of data, you can actually rewrite just the file that contains the data you need to update. So this can significantly reduce the data written. I have an example here. This is a blog that I'd written on merge on read versus copy on write techniques for the data lakehouse. And we used Uber as an example there because they had created Apache Hudi originally. Highly recommend checking this blog out or just learning more about merge on read. I think they've also brought this technique to Iceberg recently, so you can start to get some of these benefits across different table formats as well. Another thing that we do is asynchronous compaction. So this is a more advanced technique where instead of compacting data inline as it comes, you can actually have a separate writer doing the compaction so it doesn't bottleneck your ingestion. That's just another technique in general when you're running table services that do file sizing, that do cleaning up of old files, that can really help you out and help avoid bottlenecks, which can be deadly for Spark. All right, the last tip here is going into the depths of the stack, Parquet. So this is just an interesting thing that we were able to do at OneHouse that we found by playing around with the Parquet library. I thought it would be cool to share. So the problem with vectorized execution, one of them is that it only works on the extract and the transform layers. But when you're loading data, when you're writing, it's hard to do that vectorized execution. So what we were able to do is actually vectorize writes where when you're updating a Parquet file, you may have very wide columns, which is especially an important use case when you're dealing with like AI style data and you have a lot of features, like you have all these feature columns, for example. What we're able to do is using vectorized columnar merging, only update the columns that have changed in the Parquet file. So this we found gave us 4x faster execution time. And it's something that we've done at OneHouse. And I really just wanted to show because this kind of illustrates the type of gains that you can get by really just playing around with the different items in the stack here. So I show kind of down from like the engine to the lakehouse layer to even the file layer. I was talking to some folks here earlier who are also doing it at the hardware layer, which is super cool. So really just, going up and down the stack, finding optimization opportunities is something that folks should be trying to do to save on your Spark costs. One last tip I'll call out here is in doing this, we also realize that the benchmarks that are out there today don't really help with these ETL style workloads. TPCDS is old. It really only covers transformations. And when you want to be able to actually represent a real production workload, represent patterns that have updates in them, represent the scale of what you're going to need to do in production, you need a better benchmarking solution. So we actually went and built one ourselves so that we could benchmark our own progress as we tried out these Spark optimizations. We open sourced it. It's called Lake Loader. So feel free to check out the GitHub repo that's on the QR code here. And then we also released a blog that goes pretty in depth on benchmarking best practices. What are the gaps in TPCDS, TPCDI, and how can we do better? Cool. So real quick, I'll just summarize, covered a lot of material here, but think about Spark cost performance in terms of ETL. By breaking it down like that, you can actually figure out the individual components that you need to optimize. You can even look at your Spark plans and figure out how to do that. We actually released a tool that can help you with that. And I'm excited to try DataFlint too, because I think they might have some observability that could help there too. Optimize your storage, not just the compute. And then, of course, experiment with the optimizations and make sure to run benchmarks that are representative of your workloads. Whether you're doing it yourself in Spark or you're using a managed solution, you should try to figure out what works best for the type of data, type of workloads you're using. All right, so I'll open it up to questions. Just call out the things here. We have a blog on Quantum. Would love to connect with anyone on LinkedIn. And then if you're interested in that Spark analyzer I mentioned to see the different stages and how you could save on ETL, feel free to just pip install it. And we've got that can run directly within your own cloud environment. Cool. With that, any questions?
Questions?
Yep.
So I heard Databricks was investing in something called Photon, which sounds like similar to the first thing you were talking about. How are they different, or are they almost the same? Or?
Yeah, you're saying like Quantum versus Photon?
Yeah, you did that thing where you converted the vector.
Yeah, the
Oh, vectorized, yeah.
Yeah.
Essentially, it sounds the same as the Photon structure.
Absolutely, yeah. So Databricks is doing that in Photon. They're doing vectorized execution. It's becoming really popular. I see a lot of engines like starting to integrate that in, so it's really cool to see. I think that is how Databricks is able to get a lot of the gains they're seeing with Photon. Cool, any other questions?
Thanks.
All right, thanks everyone.